Welcome to This Explainer. Today, we are going to investigate a scientific crime scene that literally broke classical physics. Imagine a time when scientists thought they had the universe pretty much totally figured out. The rules were set, the math made sense, and light was universally understood to be this predictable, continuous wave. But then, a bizarre anomaly popped up in the lab that completely shattered those rules. It was a paradox that baffled the absolute greatest minds of the era. And solving it? Well, it required a total reimagining of reality.
But before we really dive into the investigation, let me ask you something to set the stage. When you hear the name Albert Einstein, what immediately comes to mind? E equals mc squared? Black holes? The theory of relativity? It is a super common misconception that his world-bending work on relativity is what earned him his Nobel Prize. Actually, scratch that. It wasn't relativity at all. Keep that in the back of your mind as we unravel today's mystery, because the answer lies at the very heart of the puzzle we're about to solve.
Okay, let's define the star of our anomaly, the photoelectric effect. The concept is pretty straightforward on the surface. You shine a light on a piece of metal and bam, electrons get kicked right out of it. It sounds simple, right? But the bizarre way these electrons behaved when they were ejected is what caused an absolute, full-blown crisis in the physics community. To study this, physicists set up the scene of the crime using a specific apparatus. They used an evacuated glass tube containing a metal surface and a detector, all hooked up to a circuit with an ammeter to measure the current. Now, normally that circuit is physically broken by the vacuum inside the tube. But when they shined light onto the metal surface, it knocked electrons free. Those negatively charged little guys would fly across the gap, hit the positive detector, complete the circuit, and boom, create a measurable current. Zooming into the microscopic level, this brilliantly illustrates the core action. Light rays come streaming in and strike the metal. The light transfers its energy to the negatively charged electrons that are bound to their atoms and forcefully ejects them away from the surface as photoelectrons. This is the emission process in action.
Now here is where things get wild. The massive conflict. Back in the 1800s, classical physics dictated that light was strictly a continuous wave. Think of water waves crashing at the beach. A bigger, taller wave carries more energy and hits the shore a lot harder. So classical wave theory predicted that a brighter light, meaning a light with a higher intensity or a bigger wave, should pack more energy and eject much more energetic electrons. But the actual experimental reality happening inside that glass tube, it didn't match up with that theory at all.
According to the old rules of the scientific puzzle, they had two major expectations. First, like we just said, brighter light should always eject electrons with way more energy. Second, even a super weak, low-frequency light should eventually eject electrons if you just wait long enough. The idea was that the wave's energy would slowly build up, kind of like filling a bucket with a slow trickle of water until the bucket overflows and the electron pops out. But nature simply refused to cooperate with that idea.
Instead of behaving, the experiments spit out 4 totally baffling clues. First, they found a threshold frequency, a strict minimum frequency of light required for any given metal. Below that frequency, absolutely 0 electrons are emitted. Period. Doesn't matter how bright the light is. Second, instantaneous emission. If the frequency is high enough, electrons are ejected immediately with 0 delay. That totally ruined the slowly filling bucket theory. Then there's the effective intensity and the effective frequency, which are so incredibly weird they need their own breakdown. And here is the real kicker, the bizarre paradox regarding those last 2 clues. When scientists cranked up the brightness, the intensity of the light, it didn't give the electrons more energy at all. It merely increased the number of electrons emitted. They just got more of them, all moving at the exact same maximum speed. But when they changed the light's color, specifically increasing its frequency, like going from red to blue light, that is what actually boosted the electrons' kinetic energy. They were flying out faster, even if the light was super dim. Classical physics was completely stumped. I mean, why on earth didn't a blindingly bright, low-frequency light work, while a very dim, high-frequency light knocked electrons out instantly? Well, it's time to bring in our brilliant detective, Albert Einstein, to explain exactly why classical wave theory totally failed here. In 1905, he looked at this bizarre data and realized a radical new approach was needed.
To solve the puzzle, Einstein focused on the metal itself. He realized that every single metal has a specific energy toll, which he called the work function. Think of it like a cover charge at a club. The work function is the absolute minimum energy required to tear just 1 electron away from the attractive forces of the metal atoms.
If the incoming light can't pay that exact toll in a single transaction, the electron stays put. No exceptions. And to pay this toll, he proposed something revolutionary. What if light isn't a continuous sweeping wave at all? Instead, he suggested it travels in localized, individual packets of energy, which we now call photons. The energy of each individual photon is defined by this amazingly simple equation: E equals h times F. E is the photon's energy, h is Planck's constant, and F is the frequency of the light. This means the energy of the light packet depends entirely on its frequency, its color, and not its brightness.
Let's build this into his master equation. Einstein proposed a strict one-to-one interaction. One single photon transfers all of its energy to one single electron. If the photon's energy is greater than the metal's work function, the toll is paid, the electron is freed, and any leftover energy becomes the electron's kinetic energy. This perfectly explains every single experimental clue. There's no delay because it's a single instantaneous collision, and a higher frequency means a higher energy photon, which translates into more leftover speed for the electron.
All right, let's put your detective skills to the test with a quick thinking challenge based on Einstein's model. Imagine you're in the lab, you set up the tube, and you shine a red light onto a metal surface. You check your ammeter, and absolutely nothing. 0 electrons are popping out. The red light just isn't getting the job done.
So you need to fix this and produce photoelectrons. You have two options. Option 1. Do you double the intensity of your red light? Just bring in a massive, blindingly bright red spotlight. Or option 2. Do you keep the light dim, but swap it out for a violet light of the exact same intensity? Which move will finally get that current flowing?
Take a second to think about it. As a hint, remember the critical difference between simply having more photons versus the actual energy packed into each individual photon. Think back to Einstein's rule of one-to-one interaction and how that cover charge must be paid by a single packet of light.
Okay, if you guessed option 2, you absolutely cracked the case. Doubling the red light just sends more photons. But because red light has a low frequency, every single one of those photons is carrying low energy. It's like throwing a million ping pong balls at a brick wall. None of them have the energy to knock a brick loose. But violet light has a higher frequency. That means each violet photon is packed with higher energy, like a cannonball. Just one violet photon has enough energy to pay the toll and blast an electron free. And that brings us right back to our very first question at the beginning of the explainer. Cracking this exact puzzle is what rightfully earned Einstein his Nobel Prize in Physics. It wasn't his famous work on relativity that the Nobel Committee cited. It was his discovery of the law of the photoelectric effect. He literally dared to challenge the established rules of continuous waves and proved that light exists in discrete, measurable packets. But here's the real twist ending to our explainer. By proving that light acts as discrete packets, particles knocking into electrons, Einstein didn't just solve a lab anomaly. He provided the absolute earliest, strongest evidence for wave-particle duality. Light behaves as a wave when it travels through space, but it behaves as a particle when it interacts with matter. This dual identity forever altered the entire trajectory of physics. This one brilliant deduction basically launched the entire era of quantum mechanics. So it leaves us with this profound, lingering mystery to ponder. If the light we see every single day is living a double life, somehow simultaneously a sweeping wave and a discrete particle, what other impossible secrets is our universe hiding? What other established rules of reality are just waiting to be broken? Keep questioning, keep observing, and thanks so much for joining me on this explainer.